Well, we considered finding radii and intervals of convergence of power series. Let us now concentrate on using the other properties from the theorem, namely the termwise integration and termwise differentiation properties. So let us now use the termwise differentiation integration properties of power series. Well, what will come out of this is the following. Okay, so far we know only one function, okay, 1 over 1 minus x, given by the geometric series, and we have equality of the two. Now, can we generalize this to other functions? As we will see, this is not that obvious. But by using the termwise differentiation and integration, we can have some progress in this. So let us recall that we have the geometric series, okay, equal to this series for every x less than 1. Okay. We are in the open interval, minus 1, 1, so differentiation integration is possible. Okay, so for some t with absolute value less than 1, okay, integrate okay, the series from 0, that's our x0, okay, to t. Well, can we do that? Yes, because in this case, the interval 0t is inside minus 1, 1. Okay. In other words, we can do that termwisely since 0t is in minus 1, 1, respectively, t0 is in minus 1, 1. Remember, in the theorem, we could integrate, okay, in a closed interval inside the open interval. Well, it is satisfied now, so we can integrate directly thus. That would be the integral of the series but now by theorem, that is by termwise integration, this is the series 0 to infinity, the integral of x to the n. Okay. Well, this is easy now. This, of course, gives us the series 0 to infinity, x to the n plus 1 over n plus 1, but 0 to t means that t to the n plus 1 over n plus 1. On the other hand, this integral is nothing but, okay, logarithm of 1 minus x. But of course, we have another minus. If you differentiate, okay, you get exactly 1 over 1 minus x. Now we have this from 0 to t, okay. At 0 you have 0, so at t you have logarithm 1 minus t. Okay. Combining together, in short, we have the following. Minus logarithm 1 minus t is actually 0 to infinity, t to the n plus 1 over n plus 1. Here, of course, as we assumed, still t must be less than 1. Now, one usually does not like minus signs in formulas, so we put t equal to, say, minus s. Then, of course, absolute s is strictly less than 1 as well, because absolute t is less than 1. So that says we have logarithm 1 plus s. That would be the negative of 0 to infinity minus s to the power n plus 1 over n plus 1. Now we could write this by putting the minus sign inside. Note that we have minus s to the power n times minus s. So combining the two minuses, we just have the sum of minus 1 to the n, 1 minus cancels with this one, times s to the n plus 1 divided by n plus 1. Okay. Now, one can, of course, write this by making a slight change. Say we put m n plus 1. Okay. Why do we do this? Just to make it look like a little bit better. Well, that means, of course, that our m now starts from 1, because n starts from 0. Well, infinity is infinity. Okay. We have minus 1 to the n, which is m minus 1. But m minus 1 is the same as m plus 1. Because minus 1 squared is 1. Okay? And we have s to the m over n. Okay. Either way, whether you use this one or this one, the long expansion is when m is 1, you have plus, so you have just s. Okay. If m is 2, you have negative, and you have s squared over 2. And it continues like that. Okay. The series converges in case absolute s is less than 1, and it's equal to logarithm 1 plus s. Okay, later we will show that from such series expansions, we could estimate the values of the function. For example, what is logarithm 2? Or what is logarithm, putting s 1/2, logarithm 3 over 2? Okay, all of these can be calculated later. But for the time being, we know that the logarithm 1 plus s function is in fact a power series. It's an infinite polynomial in this sense. Now we can play with the geometric sum a little bit more. Okay? This time, put x minus t squared in the geometric sum, which of course has a meaning if absolute x is strictly less than 1. Well, this automatically says that absolute t is less than 1 as well. Otherwise, okay, this doesn't work. So we have then 1 over 1 plus t squared is the sum, 0 to infinity, of minus t squared to the power n divided just this one. Of course, again, as I said, absolute t is less than 1. Now, integrate from 0, that's x0 here, up to s. Okay, where, of course, absolute s is less than 1. Now, this tells us that we have 0 to s dt over 1 plus t squared. On the other hand, I will not write it twice, by termwise integration. Okay, it's the series of the integral 0 to s of minus t squared to the n dt. Now this, of course, means that we have minus 1 to the n, which is a constant. The variable is t, and we integrate actually t to the 2n. So we conclude right. Okay. So, well, let us recall what the integral 1 over 1 plus t squared gave us. It's the arctangent function, because this is the derivative of arctangent. So we get the arctangent of s minus arctangent 0, but that's 0. This becomes the series n 0 to infinity minus 1 to the n times integral of t to the 2n would be t to the 2n plus 1 divided by 2n plus 1, but we put s and then 0, so it becomes s to the 2n plus 1 over 2n plus 1 when s is less than. So this tells us that the arctangent function is likewise an infinite polynomial. It has a power series expansion. Okay. Now, let us look at the whole thing from a different point of view. Let us now find the exact value of n over 2 to the n, starting from 1. Now, this is not a geometric series anymore because of this n. So, we have to think of something. Well, of course, the only thing we know at our disposal at this point is basically the geometric series. So in a geometric series, you have, for example, here, you should have 1 over 2 to the n. That would be geometric. But we want an n somewhere. Now, from the geometric series, what should you do so that x to the n gives you an n factor? Obviously, you differentiate. So, to get the factor n, from the geometric series, we differentiate. Both sides. And we get, clearly, the derivative of 1 over 1 minus x, which happens to be 1 over 1 minus x squared. And that would be, again, by termwise differentiation from the theorem, we have the derivative of the right side. Well, let us see this in long form, let us say. We would have here 1 plus x squared etc. But of course, the first one vanishes. Its derivative is 0. So that would be 1 plus 2x plus 3x squared plus and so on. In other words, we would obtain not from 0, but from 1 to infinity, okay, n x to the n minus 1. Okay. Because the constant term vanishes on the way. Okay. So we have this equality. Well, this of course says that if we put x equal to 1/2, we will be near what we want. So here, put x 1/2. Then, okay, 1 over 1 minus 1/2 squared is n1 to infinity, n 1/2 to the n minus 1. But this is clearly, if you put 2 to the minus 1 up here, it's twice n1 to infinity, n over 2 to the n. Now, this tells us, okay, let me do it here. So, okay, this would be 4, so that says n1 to infinity, n over 2 to the n is 2. Now, one can find other ways of calculating this. Okay. Well, I will go one step further. Let us find the sum of this series starting from 1 to infinity of n squared over 2 to the n this time. Okay. We expect this to be a little bit bigger, but of course, all of these series are convergent by root ratio tests that can easily be checked. So find, what I mean is find the exact value of this, okay, in a nice closed form. Now, how can we obtain n squared from x to the n? Well, one differentiation gives us n, and 2 times differentiation gives us n minus 1. Well, we have n squared in it, so this is what we do. Okay, so differentiate 2 times. Twice. That means, okay, the first derivative was 1 over 1 minus x squared. Let me write that. Okay. And a further differentiation tells us that it's 2 over 1 minus x cubed. Now, on the right side, okay, we put the derivative inside, but let us first do it step by step. Obviously, this is 1 plus x squared plus and so on. I want to write this down because when you differentiate, some terms will disappear. You may not be able to see it directly from this closed sum form. So, to be on the safe side, okay, write it in open form, check the first few terms, it will tell you what to do. Okay, so what's the second derivative here? Obviously, 1 becomes 0. The second derivative of x is 0. The second derivative of x squared is 2. The second derivative of x cubed is, okay, 3 times 2x. The second derivative of x to the 4th would be 4, 3x squared, and so on. You note that here, always, you have here this 2 times 1. So it is a product of consecutive terms. This you expect from the term-wise differentiation. If you differentiate x to the n twice, you have n minus 1, x to the n minus 2. Okay. Now, compare it with this open form to see where we start. Of course, when n is 1 or 2, 0 or 1, you have 0. So n starts from 2. Okay. And this is exactly this one. That gives us 2 to infinity n squared x to the n minus 2 minus 2 to infinity n x to the n minus 2. Now here, as we did before, we can replace x with 1/2. Of course, its absolute value is less than 1, so we can do it. Here we still have this condition. So we can put 1/2. Well, that means that the left side, which is 2 over 1 minus 1/2 cubed, is the sum 2 to infinity n squared over 2 to the n minus 2 minus n 2 to infinity n over 2 to the n minus 2. Okay. Now, when we look at this, we see that we can put 2 to the minus 2 as 4 outside. What remains is this one. Okay. But it starts from 2. We wanted it starting from 1. So this is actually the sum n 1 to infinity n squared over 2 to the n. This has an extra n equal to 1 term. Now that term is 1. That's the first term. On the right side, well, we have a similar situation. We have 2 to the minus 2, and we have the sum starting from 1 to infinity and over 2 to the n, but we have an extra term, so we have to subtract 1/2. Now let us use what we did in the previous example. This sum is 2. We found it before. So it says that 2 divided by, this is 3/2 cubed, so it is 27 over 8. That would be, okay, 4 times the sum we want, n squared over 2 to the n, minus 1/2, minus 4, 2, minus 1/2. Okay. Everything is known except this one, and one can calculate that quite easily. I will just write down the results. It happens to be 89 over 54. Okay. Now, to obtain more properties of power series, let us look at the following analysis. Okay. The power series, say 0 to infinity, an x minus x0 to the n, means, okay, again I will write it in open form. That will be a0 plus a1 x minus x0 plus somewhere you will have a k minus 1 x minus x0 to the k minus first power plus a k x minus x0 to the kth power plus a k plus 1 x minus x0 to the k plus first power, and so on. It continues. Okay. I did this because I want to differentiate. Okay. So, okay, in this case, what happens if I differentiate enough times? Well, before that, let me show this as a function. Okay, so or rather, put, let me say, define f by this. That's, you have a power series, call it f of x. We know f is differentiable. Okay. So, we can differentiate both sides. Now, when we differentiate both sides, okay, the right side is still a power series. So we can continue to differentiate f prime and then f double prime. In short, a power series, that is a function given by a power series, is not only differentiable, it's differentiable as many times as we want. Okay. So I will differentiate it k times. Okay, let me summarize my remark here. Since f prime is, again, a power series, it is differentiable. Okay. Thus, okay, f of x equal to a power series is differentiable as many times as wanted. So I can differentiate k times. Now what happens if I differentiate k times? Note that, okay, up to here, we have a polynomial whose degree is k minus 1. If you differentiate a polynomial with degree k minus 1, you get 0. So, okay, note that the kth derivative of the previous terms is 0. And the derivative of the kth term, okay, you can continue differentiating k times. Eventually, the power will be 0, which means that it's directly ak times k factorial. Easy to check. And the derivative of the terms starting with this, okay, contains some x minus x0 factor in it. Okay, this is, okay, x minus x0 times some convergence series. Okay. Why? Because you can differentiate this term-wise, and if you differentiate x minus x0 to the k plus 1, k times, okay, you have k plus 1 times k minus 1 up to 2, but the power remaining is x minus x0. So there's a common factor in all of them. Combine all three. The first k minus first ones are 0. This is known. All the others have x minus x0 term. So if we put x equal to x0, these will be 0 as well. Okay. Summarizing, the kth derivative of f at the point x0 is zeros plus ak times k factorial plus zeros again. So it is k factorial. Okay. To simplify the notation, okay, where of course the zeroth derivative means f of x. So we get ak solving directly. Okay. That would be the kth derivative at x0 divided by k factorial for every k. Now this tells us actually two things. It relates the coefficients to f, rather to derivatives of f, at x0. Secondly, okay, it tells us a very nice thing. Thus, if f of x is written as an x minus x0 to the n, and at the same time, if it's written as bn x minus x0 to the n, then an is equal to bn. In fact, they're equal to fn x0 divided by n factorial, both for every n. Okay, that's to say, a power series equivalent form for a function is unique. There's only one way you can write it. Okay, for the same x0, of course. So, a power series representation for a function f and x0 is unique. Okay, that is, AKs are directly known, okay, are fixed. They cannot take different values. You cannot write f in two different ways. If you do, an and bn will be the same. So there's only one way to write it. Okay. we can express this property as follows. If f of x is equal to this power series, then f of x is equal to the nth derivative at x0 divided by n factorial x minus x0 to b. So the coefficients a(n)s are not arbitrary. But of course, if you have the equality here, okay, this tells us to find a(n)s and, okay, calculate these this way once we know this f. So, okay, thus, okay, we can form a power series if we know, okay, if we are given a function f, which is, okay, infinitely differentiable. Okay, this means that all derivatives, or rather derivatives of all orders, exist at x. Because it's easy to form this. You calculate the derivatives, put x0, divide by n factorial. Okay. But there is a little problem. That this power series, okay, may not be equal to f of x. So we have to distinguish the two cases. That is, if we know f of x is defined to be this one, if we know equality, then a(n)s must be these. Yes. But if not the series, just f is given, and we differentiate and differentiate f and form such a series here, it may be different from it. So equality is not guaranteed. But what does all this mean? This means the following. F of x will not be equal to this one, which is actually the limit when n goes to infinity of the partial sum sequence. Okay. The partial sum sequence may converge, but not to f of x. Equivalently, okay, the difference between f of x and the partial sum sequence which is the sum n plus 1 to infinity okay, does not go to 0 when n goes to infinity. So, oh, sorry, this should be n. Right. So the difference between the partial sum sequence and f, which is this one, okay, this will not go to 0 when n goes to infinity. If it does, okay, then the limit of this will be f of x. So everything depends on this term. Does it go to 0? Okay. It is the error term. If error gets smaller and smaller, fine. Limit of this is this, so we have equality. But if we don't have equality, it will not go to 0. So the question is, when does the error term go to 0? To answer that question, okay, we have two things. Okay, two ways. Somehow we can show it goes to 0, depending on some special techniques, perhaps. Or we can calculate what that is. Well, this seems very odd, but in some sense, it can be done. This is called Taylor's theorem. Taylor's theorem tells us exactly what this error term is. Okay. And from that point on, we can continue. But before that, okay, let us have some examples exploiting this equality. Okay, as a first example, recall that arctangent of x was the sum of minus 1 to the n, x to the 2n plus 1 over 2n plus 1, and starting from 0 to infinity. In other words, it was x minus x cubed over 3, x to the 5th over 5, minus, and so on. Of course, all this happened if absolute x was less than 1, because we derived this from the geometric series. So this is true if x is less than 1. Here, obviously, x0 is 0. So question is, okay, well, actually, right. I have just one example. Okay, question is, okay, find the 120th derivative of arctangent x when x is 0. Now, in some cases, for example, in the case of 1 over x, you can find any derivative you want by direct calculation. Okay. Namely, the first derivative would be minus 1 over x squared, the next derivative 1 over x cubed times 2, and so on. You can formulate it for n. But here, you will see that even starting with the second derivative, you will have ratios and the quotient rule. And it will get quite messy, okay, directly after the second derivative. So, direct calculation is out of the question. So we cannot calculate it directly. Well, we have to use the theorem about the arctangent function. That is the power series expansion. Well, this is, of course, if we call the arctangent f of x, this becomes the 120th derivative at 0. Well, we already know that this is directly the a 120 times 120 factorial, because a 120 is this one divided by 120 factorial. Okay. So the question is, what is a 120? If we know it, we know this derivative. Of course, we will get this from the series. Okay, in the series, if we put n equal to 120, we will not find a 120. Okay, let me note this. Note that a 120 is not minus 1 to the n divided by 2n plus 1 when n is 120. To understand this, let us go back to the meaning of a 120. This is because of the following. Well, what's the expansion of f of x? It is the constant term a0 plus the derivative times x minus x0 plus f double prime x0 over 2 factorial x minus x0 squared, and the 120th derivative at x0. In general, this is 120 factorial x minus x0 to the 120 plus, and so on. This is the standard form that we got. Now, if you look at, a 120, you see that it's the coefficient of the 120th power. Okay. So, a 120 is the coefficient of x to the 100 or x minus x0 to the power 120. Okay. So we have to ask this question. So what's the coefficient of x minus x0 to the power 120 in our case? The coefficient of x minus, well, we have 0 here, x to the 120 is, let us look at this expansion. In this expansion, because arctangent is an odd function, all even powers disappear, which means their coefficients are 0. So, since in the expansion, even powers do not appear. Okay. This means that, so they are 0. And they won't be 0 for all x, So the coefficient must be 0. Thus, okay, when we go back to the question, okay, we see that the 120th derivative of the arctangent function divided by 120 factorial, that is a 120, is 0. So f120 at 0 is 0. Okay. Now, let us extend this a little bit to find the 121st derivative of. Okay. Consider to find, okay, let me say the 121st derivative of arc tangent x at 0. Okay. So the question is the same. So question is, what is a 121? Okay. This is the coefficient of x to the 121. So, okay, x to the 2n plus 1 will be x to the 121. Thus, n must be 6. Okay. So, a 121 is from the expansion of the arctangent function. Okay. This is minus 1 to the 60 divided by 2 times 60 plus 1. Okay. There's no times, that's all. This is the coefficient 121. It happens to be 1 over 121. Okay. So the 121st derivative at 0 will be a21, 121, times 121 factorial. That would be 120 factorial. Evet, burada durabiliriz.